So thanks to AI Camp for hosting this. So today we'll be talking about AI-driven language processing with doing vector search on Apache Cassandra. And today we're going to be doing it on AstraDB, which is a managed Cassandra as a service. So we're going to kick off. So just a little bit about me. So I've been a software developer for the last 25 plus years. So I'm a little bit old. It's mostly been on Java. And I've worked in quite a lot of industries, including banking and finance, obviously now doing technology, telecommunications. So I've worked for a couple of telcos. I've also done a bit of in media and advertising. But more recently, I've been doing just over the last 12 years, I'm doing community work. And mostly within the Apache Cassandra project. And just for a bit of reference, I'm an Apache Cassandra committer, so the open source Apache Cassandra project, and a community advocate at DataStax. For those of you who have some familiarity with Cassandra, you've probably seen some of my work. I respond to quite a lot of questions, so mostly on Stack Overflow and Stack Exchange. I'm quite on a few Discord servers, a few Slacks, and more recently on Reddit. And I'm part of a community that we don't just respond to questions in English. So some of the main questions that we respond to are in French, Russian, Japanese, Spanish, Portuguese, and a bit of Chinese as well. So if you've got any questions relating to Cassandra, you know, the community and I that I belong to would be responding to, I'd say, 95% of it. And we respond in quite a lot of different languages as well. So we're going to start and say with talking about what embeddings are. So hopefully everyone's, actually, before I get completely started, just can I just get a bit of indication in the chat? Those of you who have worked with LLMs before, language models, whether you're already coding in AI. Thanks, Saurabh. So we've got one who's already been working with LLMs and AI. Fantastic. So we do have a few that have been working with AI already. Fantastic. So just going to quickly run through. So first of all, what are embeddings? So embeddings are floating point numbers, otherwise in mathematics known as vectors, that are generated by machine learning models. The general idea is that you can create embeddings on things like text, video, and image, and they get converted into numerical, into numbers, just so computers can do processing on them. More importantly, we can do like comparisons, mathematical comparisons. And the encoding is done on certain features. So let's say talking about strings of text and sentences, machine learning models encode certain features which are known as dimensions, the vector dimensions. And what they're trying to do is they're trying to capture the semantic essence, the meaning of the objects or the things. So whether it's the meaning of text, or different features of the video, or certain aspects of an image. So depending on the model that you're using to do the embeddings, it will do different dimensions. It could be as little as, just the 2 dimensions, or it could be thousands of dimensions. And again, it depends on the model that you're using. Just to give a bit of an idea. So I'm going to simplify embeddings a little bit. So I'm going to talk about 4 things here. So we've got a cat, a dog, a couple of fruits, which are bananas and mangoes. So some of the features here, so I'm breaking it down in just to 2 dimensions here. One of the features is that whether it's an animal or not, and then whether it's a fruit or not. And the vector embeddings here, or the scoring, for example, for cat, in terms of being an animal, it ranks pretty highly at 0.91. But as a fruit, it's the complete opposite. So it's a negative 0.87 in this fictional scoring that I'm doing. And if we were to graph that those features, the cat appears quite low here on the scale in terms of fruit, but it ranks pretty highly as an animal. And when you look at the embeddings here, you can see that cats and dogs are have a pretty similar ranking when it comes to being an animal, but the mangoes and bananas don't rank. Actually rank pretty low, completely different end of the spectrum when it comes to being an animal. Whereas as a fruit, the banana and mango rate pretty highly. So on the graph here on the right, on the 2 dimensions, just on the fruit and animal dimension, they're pretty much complete polar opposites. But in terms of similarity, they're pretty close. The banana and mangoes are pretty close to each other, and so is the cat and dog. In terms of similarity, the way that the embeddings work, they're quite close to each other. So they're very closely related. And that's what embeddings are trying to do. So it's trying to identify, it's trying to group things and cluster things in terms of whether they're similar or not. Now, obviously, this is oversimplified. When you use something like the ADA text embedding model from OpenAI, there's a 1,536 different dimensions that they get ranked on or they get scored on. And so being able to imagine that many dimensions is something that's pretty difficult. But in a vector embedding scenario, it kind of shows you how much features there are in terms of, for example, for text. One other thing that embeddings are trying to do is they're trying to capture the semantics, the meaning of a word. So here I've got two different sentences, but focusing on just a single word, the word capital. So in the first sentence, the word capital refers to something in geography, so the capital of a country. Whereas in the second sentence, how much capital is required to invest. So the word capital in the second sentence is referring to something financial, something in a money sense, in terms of whether it's assets. Now, the word, it's exactly the same word, both capital, but they have different meaning because now the context has changed from one sentence to the next. And so if we think about doing search, traditional search where you're doing a keyword matching, you might be looking for something relating to finance for the word capital. But if you were just doing a traditional search, you return both sentences in the results. But obviously the first one is completely irrelevant because it belongs to a completely different context. And that's what vector search is trying to solve for us. It's not the traditional search that we think of anymore. So it's solving something a little bit more complex. Now, in terms of vector databases, they're specialized storage engines. They've been built for the single purpose of storing embeddings, which are the vector data type, which is an array of floating point numbers. They're designed specifically for storing vectors and then the retrieval. The retrieval bit is the important bit here because technically you can store embeddings in a text file, you can store embeddings in a PDF document, But when you're trying to search for, do a similarity search, for example, it's kind of pretty difficult to do it just in a plain text file. So it's not quite the same. Whereas if you were to do it in a vector database, it's got an engine that enables you to do vector searches. So that's the crucial thing about vector DBs. One, it can store an array of floating point numbers, which are the embeddings. And two, the really important thing is that it makes it easy to retrieve the vector data, particularly being able to do a vector search. And a vector search is what it does is we're performing mathematical comparison of the vectors. So think of I'm going to go back to the example where if we, in this talk, we're going to be using the OpenAI's ADA text embedding, which is 1,536 dimensions. What vector search is doing is that it's comparing every single one of those vectors and doing a comparison to calculate which vectors are similar, which two vectors are similar to each other. And what it's doing is it's finding the semantic similarity. It's finding the closest meaning, like the closest vector that shares similarities. We do an ANN search, which is approximate nearest neighbor. So it's a technique for finding the closest vector in terms of the similarity. There are different algorithms out there, and the main goal for this ANN algorithms is to find the closest similar vector. When I mentioned about the text, the traditional text search, ANN search is not trying to do that. It's not trying to do an exact match. What it's trying to do is it's trying to find the approximate one that's closest to the vector that we're comparing it to. And the reason for that is if we try and do an exact match, we're aiming for accuracy. But in terms of the ANN search, it's trying to prioritize speed to find the quickest, the nearest neighbors in the quickest time, but it's not going to be an exact match, so it's not going to be so accurate. So those are the important things to remember when you're doing an ANN search. Some of you would have heard hierarchical navigable small world, HNSW. It's the most popular algorithm. A lot of the vector databases use it because it's the simplest, it's the easiest to use. But we're finding that disk ANN, which is another algorithm, performs better than HNSW. HNSW tends to suffer from things like indexing problems, being able to scale indexes. And one of the things that you'll notice as you work with vector databases quite a lot with large data sets is that when you're indexing, most of the vector databases, the indexes are not immediate. The indexing is not immediate. So usually you have to wait for the indexing to complete before you can perform a vector search. And some of them can take minutes or hours to complete, depending on how big your data set is. So that can be a bit problematic. Now, talking about similarity metrics. So I'm not gonna, so this talk isn't really a deep dive into the way that the algorithms work. So this is just to highlight the different types of similarity metrics that are mostly used today. Yeah, thanks, Fernando. Yeah, so there are quite a few. So I work for DataStax, so I'm a community advocate for DataStax. So we, as a database company, as a software company, we also publish benchmarks. So yes, there are different kinds of different benchmarks available out there. and I'm happy to talk about those later on. The first similarity metric that I'm going to talk about is cosine similarity. So in mathematical terms, it's really concerned about the angle between two vectors. For those of you who have a maths degree, I'm not going to pretend that I completely understand the computation that is involved, but cosine similarity is not so good when magnitude is crucial. But having said that, there's a lot of models use cosine similarity, so you would tend to use the same similarity metric that your model is using. Vera asked, indexing is a one-time activity. Yes and no. So if you have a static data set, so which means that your data is not changing, then you don't need to re-index because your data doesn't change. But if we're talking about applications, real-time applications, say you might have a video streaming service, or you might have a product catalog, or you might have like a banking type of use case. Those kinds of use cases, and pretty much all the apps that you can think of, the data is constantly changing. So in fact, you have to continually index your data all the time. So think of like the internet giants out there that are doing like million writes per second. That means that you have to constantly do a million indexing. There's a million data points that you need to continually keep indexing. And so that's something that's very important to highlight. And I'll be talking a little bit more about that a little later on, Vera. So great question. So the next one is Euclidean distance. So this one is fairly straightforward in terms of a similarity metric, because all it's doing is it's trying to measure the straight distance between two vectors. And it's good for data containing counts and data that contains measures of things. So for example, you can do, if you've got vectors that are longitude and latitude, so and you want to do a geo search, you can use Euclidean distance to calculate the distance between two geographic points. So really handy. And the third one that is common out there is the dot product. So this one is concerned with the alignment in the same direction of two vectors. So if you think about vectors, there's a magnitude or scale, and then there's also the direction, right? And so with the dot product, it's the closest, it finds the closest vectors based on in terms of the alignment that they have. So the smaller distance in terms of alignment means that there's a higher similarity between those two vectors. And so one thing to point out is that if you can, dot product tends to perform really well because it's 50% faster than cosine similarity. Just because the amount of computation that's required to calculate the dot product compared to the computation that you need to do cosine similarity is half. In fact, when you're doing a cosine similarity, you have to also calculate the dot product. So that's something to be aware of. So I'm going to kick off with building a chatbot, just to illustrate this all. And really, my intention is to show you how it is to with vector search, it's so easy to build a chatbot against your data. And in fact, it only takes a few lines of code to get it up and running. And I'm loving the questions, by the way, that's coming through the chat. So keep asking questions as I go along. Yeah, so great question, Saurabh. So at the moment, the first implementation, so the current implementation of vector search in Apache Cassandra is HNS-W. But there's a new release coming out where it will switch to disk ANN just because it performs better. So just a quick bit of a background. So what we did with vector search in Apache Cassandra is it's using Lucene indexes. So we've kind of rewrote Lucene indexing for indexing the embeddings that get stored in Cassandra. But what we found is it suffers from one of the big drawbacks with using Lucene indexes is that it's single-threaded. So when you index, there's only one thread that's indexing. Although it's happening in real time compared to a lot of the other vector databases out there. So in Cassandra, when you write data, it automatically gets indexed. But unfortunately, there's a drawback that because the Lucene is single-threaded, we can't optimize as much the speed of the indexing, although it happens in real time. And so we're switching to disk ANN to overcome that limitation. I'm just looking at Hernando's question. Is there a natural need to canonicalize dimensions so that there are some implicit levels of portability and some roots of explainability? I'm not sure by what you mean by that. So do you mean that standardizing on an embedding model? If that's your question, then yes. Because if you're not using the same model for to generate your embeddings, then you'll tend to end up with you can't really compare the embeddings from one model to another because they're not scoring the same features. I hope that answers your question, Hernando. Right. So if you're using different models, then you mean for the language models to come up with a standard? I guess everyone does their own implementation when they write the models. Yeah, that's up to the organizations that train the models. It's up to them really. I'm gonna answer Vera's question. So talk about what happens while indexing data on the DB. So before I answer that, Vera, so I'm gonna use Astra DB today because it means that for anyone who wants to follow along, you don't have to install Cassandra to be able to do this demo because we've got a free tier on Astra DB. And there's no credit card required, so it's quite simple to create an account. In fact, before I answer the next two questions, so take a screenshot or scan the QR code that's appearing on your screen right now if you'd like to follow along. So I'm going to launch AstraDB. And so I'm going to sign in. And So I'm just gonna let this load. So just so you can see, I'm signing in quickly. And while I'm answering the question, I'm gonna click on create database. And I'm gonna create a vector database. And I'm just gonna call it my database AI camp. And I'm gonna create key space, which is the equivalent of a namespace in other databases. I'm just going to call it AI Camp as well. And I'm just going to pick the available region, which is US East. Because this is just a demo, and when you're doing like a proof of concept or whatever, you don't really care which region it's located in. But just to give you an idea, you can have a choice. If you have a paid account, you've got a choice of deploying on Amazon, Azure, or Google Cloud. And there's quite a number of regions available when you've paid. So I'm just going to click on Create Database. And that's going to take about 90 seconds. So while that's loading, I'm going to go back to the chat. So the question from Vera was, talk about what happens while indexing data on the DB. So it really depends on what kind of database. I'll specifically talk about Cassandra. So in Cassandra, everything happens in real time. So if you've got indexes created against the column in one of your tables, every time you write to that, write new data, whether it's an insert, an update, or a delete, the indexing happens in real time as well. So it's happening at the right time. That's a huge advantage for Cassandra. It doesn't happen like, 5 minutes later, it doesn't happen an hour later, it's happening in real time. Saurabh's question, vector search feature also in open source Cassandra? Yes, so everything I talk about here is about Apache Cassandra. Astra DB just happens to be the managed service equivalent of Apache Cassandra. But for all intents and purposes, it's Apache Cassandra. Oh, you want the link in the chat? Give me a second. Here we go, Benjamin. Sorry, Benjamin, I've just pasted the link in the chat. Did I paste the right one? Sorry, hang on, I didn't paste the right one. Just go back. My Astra window, and now my database is showing active at the top. So that took 90 seconds. So let me go back to the chat window. So I've answered, is it open source? Oftentimes. Yeah, that's correct, Christian. So you wouldn't typically reverse engineer the models. You would tend to just use them, unless, of course, it's an open source model, and there's quite a lot of open source models out there. You can build your own models. You can train your own models. Although I would tend to discourage, companies from doing that, because it takes a lot of computation. It takes a long time. It takes thousands and thousands of compute hours, which can get really expensive. Mill and make the vector databases that calculate vectors. So vector databases, so you can store vectors, right? So in fact, they're just floating point numbers. So you can store vectors, you can do vector searches without accessing an embedding model at all. So I'll go back to the classic example of longitude and longitude. So those are just geographic coordinates that contain floating point numbers. They're vectors. It's a two-dimensional vector. You've got a longitude floating point number and another floating point number for latitude. And you can do vector search. You can do Euclidean distance computation on them without touching any embedding model, right? So so you can do that with a vector database. So the vector search engine and the capability to store vector types is built into the vector database, but the model is not. So for context, it's not calculated. Yeah, exactly. So that's you got that, Milan. Another question, Jonathan. So Jonathan has the question. So Apache Cassandra seems like the obvious choice for scaling and unstructured data. Actually, Apache Cassandra is used for anything and everything, not just unstructured data. And typically when I think of unstructured data, it's like JSON documents that don't have, predefined schema. You can store those in Cassandra. Most developers store them, that work with JSON documents, store them in MongoDB. But when you have massive amounts of data, MongoDB becomes problematic because it doesn't scale as well compared to Cassandra. So a lot of organizations move across to Apache Cassandra. And in terms of GraphDB, so Cassandra is a multimodal database. So in fact, you can store graph data in Cassandra. And in fact, DataStax Enterprise, the enterprise version, the enterprise software that's built on top of Cassandra has DataStax Graph. So you can use like Gremlin and Tinkerpop to do like graph computations on your graph database. And that's running on Cassandra. Yes. Perfect. All right. So now I've got this. So I've created my database and my database is up and running. So because I was answering questions, I wasn't able to show this in real time, but it took about 90 seconds to create a vector database cluster. So AstraDB is a cloud native, fully managed Cassandra as a service. And so it's running on Kubernetes. And in less than 2 minutes, just with 3 clicks, I've managed to launch a database, didn't require a credit card. I've got a full Cassandra database operational with multiple nodes, and you get all the high availability in less than 2 minutes. In fact, it took 90 seconds to launch the database. So it's great. So on the free tier, I've mentioned in this slide that you get $25 of credits per month, which is equivalent to about 70 million reads or 40 million writes. So for some organizations, that's kind of like the equivalent of their production workload, which we give away for free on AstraDB. So just so you can develop stuff without being bogged down with having to download and install Cassandra. So now I'm going to go to the demo. So just quickly, it's a RAG demo for AI chatbots. And what I'm doing is, what we're going to be doing is we're going to store data into the database, and we're going to use OpenAI's, models and we're going to augment the data that's supplied to OpenAI, so it can give us answers that's based on the data that we already have. So let me paste this link. For the demo, for those that want to follow along. So I'm picking the very first one. So there's quite a number of examples here. I'm going to pick the first one. So we're going to do this in real time. Okay, so this is a collab notebook. So some of the stuff is not fun. So we're going to install a few libraries. It's okay if you don't know Python. So I'm just going to quickly explain. So we're going to install an OpenAI libraries, some pandas, which allows us to work with different kinds of data. We're going to install the Python Cassandra driver into this notebook so that we can connect to the Astra database. And the final library that we're installing is called datasets, which is a library for interacting with Hugging Face. So I'm just going to go and install that. While that's installing, that will take about 25 seconds. I'm going to click on the connect for the database. We're going to generate a token. So this is so we can connect. So here's the token that it generated. So really important that you save this token. So this is the particular token that we need, the one that starts with Astra CS to connect to the database. And always download your token once you've generated them, because you won't be able to get access to them again once. So if you've used other services out there, you can only see the token once you've generation time. You won't see them again once you've left the screen. So let me just save that token somewhere. Okay. And the other thing too that I'm going to do is I'm going to click on Get Bundle. So I'm on the Connect tab of my database, and I'm going to click on the Get Bundle. So this is the Secure Connect bundle. And this one contains, so think of this as the database URL, like a JDBC URL or something like that, that tells you how the connection to your Astra database that's running on the cloud. But more than that, the secure bundle also contains the certificates for authenticating to your cluster. So got my secure bundle, downloaded that, and I'm going to go back to here. So here it's installed all the different libraries, the Python libraries that we need for this demo. And now I'm going to run the import for the modules. That's really quick. And so now here, the next one is we need to save the details. I'm just retrieving my token. Second. Okay, so I'm gonna I'm going to input my token. Now, one thing I didn't show you is the OpenAI platform. So I've got an OpenAI account. So I'm hoping that you know, the rest of you would have used ChatGPT, which means that you would have had an OpenAI account. And so if you just go to platform.openai.com, you can go into your under your profile, you can view the API keys, and you can create an API key right there. And so that's the API key that we'll be using here. So once you've created your API key, use that API key, and we're going to store it as an environment variable. The key space name, when I created the database, I've called it AI Camp. So I'm just going to put that in there. And so I'm going to run this next one, which would have stored it in here. So the environment variables, that's just what we've done. So we've just store the environment variables. Okay. All right. So now the next thing I need to do is upload my Secure Connect bundle. So just so this notebook knows how to connect, oh, hang on. How to connect to the database. So again, the Secure Connect bundle, think of it as like your JDBC URL. And so for the purposes of this demo, we're going to use OpenAI's ADA text embedding. So we're using the second generation model. So we're going to load that as an environment variable. And then finally, we're going to create a session object to the cluster. And if we've done everything right in the previous steps, it will give me back a session, just so I know that we're connected to the database. Otherwise, we'll get a few errors. Like, for example, if you've mistyped the AstraDB token here. In fact, let me make that bigger. So far, we're just doing a few setup. So before I create the database schema, just gonna quickly show. So I'm just gonna jump to the data set that we're gonna use. So it's gonna come from Hugging Face, and it's called Squad. So it's a question and answering data set from Stanford. So we're just gonna load that. So this is just just so our database is not empty. We're just trying to populate the database for this step. So this isn't something that you would normally do because you would already have data in your database. So we're just downloading the data set from Hugging Face. And so this is what it looks like. This is what the data looks like in there. Like that. So it's got an ID. It's got an ID. It's got a title. It's got a context, which is also a string. And then there's a bunch of question and answers. So in fact, for the same title and context, there's multiple question and answers on this side. So we're gonna go and simplify our data set, and we're gonna remove the duplicate. So we only want one title, one context. So that's what this step is doing. We're just doing a bit of a cleanup. And so if you look here now, we've only got one context, whereas if I scroll up here, you've got 5 of the same context. Whereas after we've cleaned up the duplicates, that context, there's one context, one title, a different context, and so on and so forth. So we've got just different text here. Okay, so just to go back, so we've got an ID, a title, a context, a question, and an answer. So I'm gonna go right back up to where we create the database schema. So I'm gonna create a table called squad, and it's got an ID, a title, a context, a question, and a bunch of answers, which is a collection in key value pairs. It's in Cassandra, we're calling it a map collection. And then the last field or column in that table is going to be an embedding of the title and the context put together. And we're storing that embedding in a vector data type. And as you can see, the dimension here is 1536, just because the model that we're using, the ADA model from OpenAI, the text embedding model, has 1536 dimensions. So that's how big the vector array is. And then we're also creating an index on that embedding so that we can do similarity functions. And for this particular index, we're going to use dot product. Again, it's 50% faster than cosine. So I'm going to run this. Okay, so now that it's created the database schema, we've already downloaded the data. So we're going to go and now load that data into the database. So in here, it's going to iterate over the different rows. So the data object we've already loaded here, up here. So we've created this data object. And so that's the data object that we're acting on in this app. So we've got the data object. We're going to iterate over the rows. There's 300 rows that in this data set. So we're only using the subset. And we're going to do, so the chunks that we're going to feed into the model is a combination of the context and the title in the table. And we're going to use this code, this API call to OpenAI to generate the embeddings on that chunk. And we're going to store it in the database. So we're going to do an insert once we've created an embedding for that, for the context and title. We're going to insert it into the database. So, and it's a big difference with using Cassandra as a vector database. We're storing both the data, so the ID, title, context, question, the answers, and the embedding together, right? Very, very crucial, because in other vector databases like Pinecone, they're a one-trick pony. All they can do is store the vectors. They can't do anything else. And that's problematic because you need to have 2 separate databases. So one database to store your data, and then another database to store your embedding. And so one of the biggest problems that a lot of once you start using vector databases is you realize that trying to keep those 2 different databases in sync is problematic, particularly when you have to scale up and you're doing 1 million writes per second. You don't have that problem in Cassandra because Cassandra stores both the regular data and the embedding together in the same table. And so this embedding here, that variable that we create contains the embedding from the OpenAI call is the same one that we're gonna insert down here. And so this, I'm gonna modify this code so that it doesn't do a sleep. So if you've got an OpenAI free account, you're rate limited at 60 API calls per minute. Because I've got a paid account, I don't have the rate limit, so I'm gonna disable this throttle that sleeps for 60 seconds. So I'm gonna run that just to insert the data. So all we're doing at the moment is we're just preloading the data into the database. So we're just loading it up so that we can do vector search against it, just so we've got data in the table. So I'm just gonna click back here. I'm just gonna click on the SQL console so that we can run SQL queries. So I'm gonna use my AI camp key space, and let's see how much is in the database right now. So there's 59 rows at the moment. While this is running, so this is just to show you that we're loading up. There's 74 now. So I think this one to insert, so the thing that takes the most time in this piece of code is generating the embedding. So you can see that it's constantly stuck on this one. That's the one that takes the longest time. So to insert the 300 records, it will take about 60 seconds, just because we're doing API calls across the internet, making calls between OpenAI and the internet. And actually, in fact, it gets worse than that. So my database is based in the US East, in Melbourne, Australia, and we're making calls across the internet to OpenAI. So that's where the latency is coming from. So that's still inserting. It's 198 now, so nearly there. A few more seconds. 221. So if you have a free account, this will take, anywhere from 6 minutes to 10 minutes to generate the embeddings and insert it into your database. But because I've got a paid account, it's a little bit quicker. 264. Nearly there. 282. You're welcome, Hernando. I love the questions. So that completed in 2 minutes. So just to check, yeah, so we've got 300 records in the database now. Okay, so, and we stopped writing at 300. So just so this is what it looks like. This is all the stuff that it's inserting. Okay. And so now here's the fun part. So this is the bit where we're building a chatbot. So here's the, as a user, this is the question that's being asked. When was the College of Engineering in the University of Notre Dame established? So we need to generate an embedding for this question. And so we need to make another OpenAI API call to create the embedding against this customer input here. And so as you can see, this is the actual embedding. So these are floating point numbers. And as I mentioned earlier, for this model, there's 1,536 different dimensions. So that's how many floating point numbers get generated. Can you reconfirm what to be added from the secure bundle zip file? So the secure bundle zip, so if you're on your AstroDB, you click on the Connect tab, and you can get the bundle here. And that bundle is what you need to upload to the section here about environment variables. So you key in your token, your OpenAI API key, and then you run this bit to upload the secure bundle to your notebook. Hopefully that answers your question, Himana. So going back, so we've generated float embedding for the question. And so now we can do a vector search on that question to query the data that we already have. So here's the vector search. So select from squad, so that our table is squad. So for us, because we're using Cassandra database, it's only a single database call. If you were using something like Pinecone, you have to do a select on your database, and then you have to then do a vector search against Pinecone. So that's a second. So that's a second query that you have to execute within your application. And once Pinecone returns a result, it will tell you, for example, it will give you the 3 results, right? And it will tell you vector 1, 2, 3 and vector 4, 5, 6 are the nearest vectors. So then you need to do another lookup on your database to get the data that relates to those vectors. So you have to do 3 different queries to do exactly just the one thing that you can do within Cassandra. So here's the vector search. So we're doing a vector search against the title and the context embedding, and the ANN search on the embedding. So the embedding is this embedding that we did at the top here, and we just want to return the top 3 results. So I'm going to run that vector search, right? So in that vector search, because I'm searching for similar vectors, it's going to return vectors as well. And in fact, there's 3 lots of 1,536 vectors, because remember, each vector embedding that we have has 1,536 embeddings, and we've got 3 results because we asked for the 3 nearest ones. So that's what it did. And just to show you what those three results are, so we're going to execute that query again that we had up the top here, but this time instead of displaying the embeddings, we're going to display the context from those embeddings. So I'm going to run the same query, but just displaying, instead of displaying the floating point numbers, I'm going to display the context. So this is the data that's stored in the database. Okay, and it's come up with 3 different results, 3 different rows. Okay, so far, okay, so what do you do with it? Well, we're going to build a chatbot that accepts questions from users and returns answers, but instead of ChatGPT giving random answers, it's going to give the answers based on the data that we have on the database. So what I'm showing you here is that you can now do natural language questions against your database instead of doing traditional CQL or traditional SQL. So what we're going to do here is we're going to build a prompt. So this is a specific thing for OpenAI. So we're going to build a prompt that has a role. So the system, so this is the AI assistant. We're telling the AI assistant that it's a chatbot that's helping customers with questions. So in fact, you can in OpenAI, you can tell the system different things. So for example, you can tell it in the content, you would say, you're a funny chat bot that gives rude answers to customer questions. And when it writes the answers, it comes out rude, but it still gives you the correct answers. But we're going to be nice here because we're doing a demo. So it's just a chatbot to help with customers. And then another object in the array is that we're going to create a user. So this is the one that has the customer input, which is the question. And the question here is, if I go back up the top here, the question is, the question here is, when was the College of Engineering in the University of Notre Dame established? So that's the customer input. So that's what we're giving to the OpenAI model. And then the next thing we're going to do is we're going to pass an array of answers. And these are the top 3 answers that we got up the top here. So these top 3 results that we got from the vector search query against the database, we're going to provide those top 3 results to OpenAI. And we're going to give it the context so that we want OpenAI to give the answer based on these 3 results. So this is retrieval augmented generation. So we're augmenting the Gen AI that's generating answers based on the data that we give it. And so finally, the chatbot, which is the AI assistant that we have, is going to give this prompt when it answers. So here's my answer to your question. And for this demo, we're using the GPT 3.5 Turbo model. Let me take that out. And so let me run this bit of code. Yes, so Jonathan, yes, that's correct. So I only generated the top 3 results. You can generate the top 10, you can generate the top 100. It's up to you. But just for the purposes of this demo, we're just using the top 3 just so it's quick. And so here we are. The response from ChatGPT is that the College of Engineering at the University of Notre Dame was established in 1920. Now, that answer didn't come from ChatGPT itself. It came from our data, the data in our database. So we've fed it knowledge about our data, and so now we can just continually keep asking questions, and then feed it to the chatbot so that the chatbot will provide answers based on the data in our database. Yeah, so that's one of the links that let me do it here again. So, so there it is, Ivan. So it's the first one in the list. And just in case you're gonna ask, I'm gonna post this as well. So here's the AstraDB URL as well. So Jonathan's question is, he tried ChatGPT at the same time. So this answer that we've got in the demo didn't involve ChatGPT. We used OpenAI. Okay, and we used OpenAI's GPT 3.5 language model. And so we fed it the data from our database to come up with this answer. So when you ask ChatGPT had one of the things that I probably should have pointed out is that this squad dataset from Hugging Face is actually question and answers from Wikipedia. So so you can see here it comes from Hugging Face. So the downside is that when ChatGPT trained on the 3.5 turbo model, they pretty much scraped the whole internet, including Wikipedia. So it came up with the same answer as well. Does that make sense? All right. Yeah, I know, it's funny, right? So let's go back to this. So we've done that demo. So now I'm gonna push on. So here's the important thing. So I've mentioned it quite a few times, and in fact, thanks for the very fantastic questions, because it just keeps reinforcing that not all vector DBs are created equal. So the big thing about using Apache Cassandra as a vector DB is that you're storing regular data together with the embeddings in the same tables. You don't do that with other vector databases, because most of the vector databases that you're doing there, that is out in the wild, like Pinecone, they can only do one thing, and that is storing. Hemanath posted, he's getting you exceeded your current quota. Yeah, that's because you're using a free account. And so you've probably used up all your quota. So when you do an API, yeah, so you can't bypass it because you've run out. So unless you pay, you won't be able to. So if you want to do another demo, so you've exceeded your quota. I think it lasts for a whole day, so you might be able to do it tomorrow if you've exceeded your quota for today. So going back, so Apache Cassandra, you can do regular database queries because your data is stored in a regular database. But more importantly, when you're using it as a vector database, you can do vector search. And the biggest thing about it is that you can do a hybrid of both. If you're using something like Pinecone, all you'll be able to do is vector search in Pinecone. You can't do a hybrid of regular data, combining the results of a regular database query and doing a vector search on top of that in one single call. So the question about OpenAI's APIs, what about the data privacy? So at the moment, when you create an OpenAI account, it tells you that you own your data, but it also stores the history of your queries. So if you're using ChatGPT, it's actually learning from you while you're using it. That's why there's nothing, no such thing as free lunch, Yehuda. So ChatGPT is letting you use it for free because they want to learn about how you're using it. So that's the downside when you're using something like a free service at the moment. And so one of the things too that I keep talking about earlier, so going back to the slides, data is indexed at the right time, which means that the indexes are available immediately. You don't have to wait. If you compare it to other vector databases, you might start loading data, you're writing, and then you have to wait for those indexes, for the indexing of that data to complete before you can perform vector searches. So huge downside. Imagine if you're writing, 1 million data points per second. You're constantly having to wait. Whereas in Apache Cassandra, because it's happening at right time, you can query in real time. You can query your data immediately. And here's the one of the biggest points too. So Apache Cassandra has been around for over 10 years. DataStax as a company has been around for over 11, 12 years. And so when you think of vector databases, you know, you need to when you're making a choice in terms of which vector database you're using, you need to, make sure that you go with someone you can trust. You want someone with a track record of, providing high availability, reliability, and being able to scale, right? So particularly, startups, for example, they always think you don't try and deploy onto something that doesn't scale, because think of the situation when your application, like you might have a mobile app that goes viral, and suddenly you've gone from 10,000 users to 1 million users overnight. If your platform is not backed by something that has the ability to scale, your app that went viral overnight is also going to crash overnight. And so think about that when you decide to use like a vector database from a company that's only been around for a few months, because really what you're doing is you're beta testing in their database in your production environment. You're testing their database for them. That's what you're doing. And so with something like AstroDB, which is a managed service, it's built on Apache Cassandra. So, it's all got the good things that you have, except that you no longer have to manage it. The big advantage too with AstroDB is it's got a direct LangChain integration that uses the Cass.io library. So in fact, you don't need to worry about the database side of things, because LangChain will take care of you through the Cass.io library. And for those who are JavaScript developers, there's also a JSON API that has Mongoose JS integration, which means that you can, you can build your applications without having to worry about the database, because all of that is taken care for you. And in fact, there's a Stargate Mongoose driver just for those who are interested, who are JavaScript developers. There's Mongoose support for Stargate JSON API. So it's completely open source. It allows Mongoose developers to use Cassandra without having to change their code. So you don't have to rewrite your application. You just have to do 2 lines of code, and then suddenly you're now connecting to a Cassandra database. Just really quickly, so Stargate is an open source data API gateway, which allows you to perform CRUD operations on your Cassandra database just using APIs. So we've got REST APIs, GraphQL, gRPC, and also the JSON API. So the JSON API lets you do save and search schemaless JSON documents in Cassandra. Again, it's fully open source. It's in, you can find more information about it from Stargate.io. And just checking the chat if there's any more questions. Yep, okay. If I'm happy to stay around if anyone's got any more questions, but otherwise, thank you very much. Really appreciate you all for joining us for this session and allowing me to present to you all about Cassandra. Thanks, Edith, appreciate it. I know it's either late or early for a lot of you, so thank you for joining me for the live session today. Let me know if you have any questions. You can catch me on Stack Overflow, on Stack Exchange. Thanks, Dan. Thanks, Anita. Thanks for the questions, Jonathan. Appreciate it. Thanks, Lawrence. Thanks, Yehuda, Emanath. Thanks for your questions. Daniel, Irish, appreciate it. Thanks, Milan. Yes, Yehuda, there will be a recording that will be shared, and we'll include the slides in that too. Thank you. Thanks, everyone.
Thank you so much, Erick, for the amazing session. I think most of the people enjoyed it. I am seeing a lot of comments, happy, attendees. So thank you again for speaking and explaining the concepts.
Thank you for having me.
Yeah, sure, no problem. I think we have more questions coming.
Yeah, so Saurabh, vector search in Cassandra, it's designed for internet scale. So, it's it can handle billions of vectors. In fact, we talk about using Cassandra as a vector database with petabyte scale. So, you can do 1 million reads and writes per second. Awesome. Thanks, Saurabh.
Yeah, Usama has a...
Yeah, so Mohammed's question, so explain again how ChatGPT was able to narrow down to one answer. So that's what the GPT 3.5 Turbo does. So you feed it the data, and based on that data, using natural language, it will try and come up with an answer for you. That's how the model works. Now, so it's not actually ChatGPT, it's an open AI GPT model. Because when you talk about ChatGPT, we're talking about the one where you go on a web, the open AI ChatGPT webpage where you ask questions. That's actually not the same one that we're using. So we're using one of the GPT models, one of OpenAI's GPT models. Now, how it works, that's a black box. That's not open source, so I can't tell you how OpenAI does it. Saurabh, yes, I've heard that. Yeah. So, and that's the thing. So that's why I say that not all vector databases are the same. So you will hit limits. Whereas Cassandra has been around for, since 2008 when Facebook open sourced it. And most of the tech internet giants use it. The poster companies that we use are like Netflix and Apple. They choose Cassandra because they need the scale that Cassandra provides. And so if performance and scale matters to you, then you choose Cassandra. Now, having said that, I'm an Apache Cassandra committer. So, of course, I'm going to be talking about Cassandra. But that's why I chose Cassandra in the first place. But that's a good question.
Okay, great. I think there are no more questions. Yeah, thank you so much, Erick. We'll be wrapping up the session. We already went a few minutes over. I didn't want to stop you. Okay, take care, guys, and stay tuned for our events.